State the definition of an infinite decimal in base 10 and prove that an infinite decimal must converge to a real number. An infinite decimal is typically wrote like b dot e1, a1, sorry, a2, a3, and so on. And this is associated with the real number b plus summation j equals 1 to infinity a sub j over 10 to the j. And we have some stipulations on the b's and the a's, where b is a integer and typically a positive integer for the definition to work as stated. And all the a sub i's are integers, and they all lie in between 1 and 9. You'll notice that this is for positive integers. I'll let you think about what the definition would be for a negative decimal. It's not quite what's written on the screen here. Okay, now why must this converge? Well, this is an infinite sum, and so there's no guarantee that this converges. So theorem, this infinite sum converges. And the proof is basically by the dominated convergence theorem from calculus 2. Summation j equals 1 to infinity a sub j over 10 to the j. If I take the absolute value of this, well, it's always positive, so the absolute value is superfluous. So the absolute value just goes away because the a's are positive and 10 is positive. Now this is strictly less than or equal to, well, I shouldn't say strictly, it's less than or equal to summation j equals 1 to infinity of 9 over 10 to the j. And this series converges by the root test, by the ratio test, and we can actually get it exactly because it is a geometric series. The first term is 9/10. If I plug in j equals 1, over 1 minus the common ratio, and the common ratio is 1/10. And I'll let you convince yourself why that's correct. And that's equal to 1. So this series is less than or equal to another series that converges. So by the dominated convergence theorem, from calculus 2, or more technically from real analysis 2. So by the dominated convergence theorem, this series converges. Let me just copy it over just because that's the conclusion. By the dominated convergence theorem, this series converges. And that is the end of the proof.